Today we're going to be looking at what we call balancing equations. And it operates under this rule that matter cannot be created or destroyed. All you can do with it is change it from one form to another. So that means that when we have an equation like this for assembling our old buddy water, H2O, out of its component elements, H and O, we have to balance the equation, meaning that the same number of atoms have to appear on both sides. They can't just disappear or appear. And before we go much further with this, let's take a look at these two guys right here, because they are what we call diatomic gases. And any elemental gas exists like this, exists diatomically. So be careful, because anytime you see a gas that is one element, chlorine gas, fluorine gas, nitrogen gas, they all have to exist like this. It's just a fact. And we'll make sure that we indicate that they are gases with this little lowercase g, because that just, that's what they are. They're a state of matter, they're a gas, and that when they make water, it's going to be a liquid. We'll indicate that with a small l. So if you see that, that's what those mean. All right, so anytime we have a gas that is an element, it has to be diatomic. That's just a fact. Like the sky is blue and water is not wet and all that stuff. All right, so here's how this works. If we have a certain number of an element on one side of the equation, it has to exist in the same number on the other side. And here is an example. In this equation, there's only one atom of oxygen on this side, but over here, this little subscript tells us that there are two atoms of oxygen on the left side. So we need to balance this, and we cannot change subscripts. So we have to leave them the same. What we call subscripts, they are part of the molecule of a formula. In other words, they tell us what the ratio of elements is, and so they cannot be changed. But what we can do is we can add coefficients, and a coefficient is a multiplier. All it tells us is how many of each of these molecules we have. So we can't change subscripts, but we can add a multiplier. And let's take a look at what we mean. Over here, there are two oxygen atoms, and we can't change that subscript. Over here, there is one oxygen atom, and we can't add a subscript to that, but what we can do is add a coefficient. We want the number of oxygen atoms to be the same on both sides. So since there's two on this side and only one over here, let's add a multiplier of 2. And this multiplier multiplies the whole molecule. So there are now two atoms of oxygen on this side here, and because there are two oxygen atoms on this side, the oxygens balance. However, because we put this coefficient of 2 over here, we also have multiplied the hydrogens. And this coefficient of 2 is multiplying the fact that there were already 2 atoms of hydrogen, which means there are now 4. So to add to make sure that there are 4 atoms of hydrogen on the other side, let's put a coefficient of 2 next to this one. So what I always do when I want to double check is I like to count these up. And I'll say, okay, we've got 4 atoms of hydrogen on this side, because 2 times 2. We have 2 atoms of oxygen here, and that means that there should be 4 atoms of hydrogen on this side, which there are, and 2 atoms of oxygen here. This equation balances. Here's another way to look at it. This is an equation for assembling the molecule ammonia. We're making it out of nitrogen and hydrogen. And notice that nitrogen and hydrogen are both diatomic gases. They both have these subscript 2's, indicating that there are 2 atoms of nitrogen here, 2 atoms of hydrogen here, and we can't change those. On the other side is the ammonia molecule, which has 1 atom of nitrogen and 3 atoms of hydrogen. I'm going to start off by putting 1 of each of these molecules in this equation. And right off the bat, it says right here, whoops, I didn't mean to do that. It says right here that there are 2 atoms of nitrogen on this side of the equation and only 1 on the other side. So this side of the equation is a little heavy with nitrogen. That's these blue atoms here. Hydrogen is looking a little heavy on the product side because there are 3 atoms of hydrogen on the product side, and yet on the reactant side there's only 1 molecule of hydrogen. That means 2 hydrogen atoms. So I have to somehow increase the number of nitrogens on this side. Well, there's 2 here and only 1 here. So I'm going to multiply this molecule by 2. And check it out. Our nitrogens are balanced. 2 on the reactant side, 2 on the product side. But by multiplying this molecule by 2, I increase my hydrogens as well, because this subscript tells me that there are 3 hydrogen atoms per molecule, and I just multiplied the whole molecule by 2, so now there's 6. So how can I get 6 atoms of hydrogen on the reactant side if there are 2 in a molecule? I'm going to multiply this molecule by 3, and now my equation is balanced. Let's try one more. This is a reaction for the combustion of methane. It takes a methane molecule, CH4, it reacts it with an oxygen molecule, O2, it produces a carbon dioxide molecule and a molecule of water. Let's start by making sure that we've got 1 of each of these molecules. Right off the bat, it says that the carbons are balanced. There's 1 atom of carbon on the reactant side, 1 atom of carbon on the product side. So that's in good shape. However, the hydrogens are way out of whack. There's 4 atoms of hydrogen on the reactant side and only 2 on the product side. And the oxygens are out of whack too. There's 3 atoms of oxygen on the product side and only 2 on the reactant side. I usually save oxygens for last. So what I'm going to do is I'm going to fix the hydrogens. And since there's 4 on this side and only 2 on this side, I'm going to multiply this molecule by 2. And what's nice is that that balances the hydrogens. But because I multiplied this molecule by 2, it multiplied the oxygens by 2. So now there's 2 oxygens in this side and 2 oxygens in this molecule and 2 here. Well, there's only 2 on this side because we only have 1 molecule of oxygen. So I'm going to multiply this one by 2, and that brings everybody into balance. Let's go back and we'll do one more by hand on this other sheet of notes. So this one says, balance the equation for the synthesis of aluminum oxide from aluminum and oxygen. That means we're going to take solid aluminum, that little s means that it's solid. We're going to react it with oxygen, which is a diatomic gas. Every time we have an element all by itself, it's always a diatomic gas if it's a nonmetal. And the product is Al2O3. So, right off the bat, I can see that my aluminums are out of whack because there's 2 aluminums over here and only 1 on the reactant side. So what I would normally do is I would say, I'll put a 2 here. But right off the second bat, that throws off my oxygens, because according to our coefficients, according to our subscripts, there's 3 oxygens over here and only 2 over here. So I'm going to get rid of all that stuff and start over. Let's try it with the oxygens first. So because I have 3 oxygens over here and only 2 over here, let's use a common factor. Let's multiply this one by 3 and this one by 2, and that makes 6 oxygens on both sides. But because I added this coefficient of 2, that also multiplies the entire molecule, and since there were already 2 aluminum atoms, now there are 4. So I want to multiply this aluminum by 4, and that balances the equation. Let's double check. 4 aluminums on this side, 4 aluminums on this side. Cool. 6 oxygens on this side. This 2 multiplies this entire molecule, so it also multiplies the subscript for the oxygen, and that means 6 oxygens over here, and we are balanced. Okay? Take it for a spin.